My hat! Alright, so here we go. Traxxas picked it up. I finally was able to remove this back plate, so I had to use my rotary tool, an actual Dremel. I'm going to have to straighten this out just so I can rebuild it. There's a plastic shield that goes right here, protects that. Here's the bearing, there's the sensor board, and oh, this is on the stator. Is this plastic? Let me see if I can remove those. Next thing you know, it'll break and I won't be able to work with it. Let's see if I can remove the rotor. No. All right, well. All right, so there's a shim right before the fan, right here, and then there's this other shim. Looks like it's nylon. I'm not sure if this thing is just warped from this. This thing probably warped from me banging this out. Now the fan, I'll have to remove the bearing. But right here on the shaft, there's these little key points. So when this thing goes in, it just keys in, clips, and that's what keeps it from not spinning. So I guess this is what locks it and makes it spin. So this is your fan right here. So I need to remove this, and then I can take a gauss reading. It'll be interesting because you can see the magnets inside, and then you have these laminations on the outside. But let me remove these and then I'll grab a common rotor and then you'll see the difference. But here's all the balancing. So the balancing, you can see where they removed material in order to balance. So that's actually quite a bit of material they had to remove in order to balance this rotor. All right, so this is the stator. So the stator is the part that doesn't move. So I just cut the housing. That's the easiest way instead of getting rid of that epoxy. I guess if I had a press, I could have pressed it out. But anyway, I was destroying this motor. So it doesn't really matter, but let's see, laminations. So if we look at the laminations here, we're looking at about 2790. 2792, still pretty good. Let's see, 2788, 83, 28. Am I measuring this right? There we go, 2797. So I'm just going around 2787. Yeah, they're all, for the purpose of this, they're even. I'm gonna say they're even, which is pretty good on the laminations. Now the inside, so if I measure the inside, I'm just gonna go, let's see, there we go. So here, this is, let's see, where should I measure from? I guess I can measure from the internal laminations, maybe, if this thing will reach. Let's see, it's about 1693. 1673, let's see, it moved. 1705. I'll remeasure the last one. 1671. And the first one will be the last one again, just to make sure. 1692. All right, so that's what we have on the inside. So now what I'm going to do is I'm going to cut this and I'm going to count the turns. All right, so let's see. There we go. All right, so there's 2 strands of wire. Oh, I see. One of them's going to a different. There we go. So this is the one. I'll go ahead and just remove this one and see how many turns. I could cut this, crack it open. That might be easier. But let's see if I can do it without doing that. So that's okay. So this is 1. That's 1 turn. Two.
I decided to speed this up 8 times, so if you slow it down 8 times, you can count along. As fun as it was to count with the count in Sesame Street, I figured I'd just speed through this thing. But what I'm doing is I left half the strand out, and then I just sort of pull a little to go over the loop, and then I just pull out the back end, so all the wire just keeps going. So every time I pull from the back end like that, that's a whole turn. That's an entire turn. So that's how you know. So if you go back, slow it down, every time I pull it with my hand back, that's a full turn.
That's it. So that's a turn. Now I'm starting to undo the second one. So that's the half turn. That's why you always get counts in halves, because 1, 2, 3, 4, and then it ends over here, it goes to the next one. But there we go. Although this wire was on that side, so that would be a full turn. It's interesting. Oh well. So we're going to do the other one. So this was over here, so I'm half a turn right now, and I will pull.
So I cut off the initial wire and then I counted them again. I got the same number, so I'm not sure if it would be 14 or 13.5.
13. I mean, it loops all the way around, so you could say 14, but it's a 13.5 turn. So now, if I'm going to pull this down, that'll be half a turn. Do it again. That's the half.
So the way I'm counting this is I'm taking just half a turn out so I can pull on that, then I'm pulling with the pliers just so I can go over the loop, and then I pull back with a hand. So every time I pull back with the hand is a full turn. Now I keep counting the first half, 13, and then the other half that goes up, so that would be 14 complete turns. But I don't remember on the other motors, because the other motors tend to end on the opposite side, which is where you get the 0.5. So I'm going to say 13.5 in this video, but it could just be 14 because I'm counting wrong, or because this motor is just wired. It starts and ends in the same spot where I'm missing something. I probably just don't know how to count turns. That's the reality. But anyway, if you want to compare it to motors, the closest thing would be a 13.5 motor if you're looking at common motors. So keep that in mind.
So that's the half and the 13, and then I start up on top again. Well, I mean, it loops back around, so that'd be 14. If it loops back around, then I go again. So this would be equivalent to, say, a 13.5 turn motor, as far as regular motors are concerned. Although it does loop all the way. But I've not taken one of the other motors apart, so that's something to consider. I'm curious. 0.69. I'm not sure what this corresponds to in gauge. I'm sure there's a table out there. 0.69. .67. Trying to measure where there's no kinks. 0.65. 7, 6, all right. So about 0.67. Yeah, roughly 0.67. So the wire is pretty good. I wonder if at 65, maybe I was pressing on it a little too much. This is it. This is how motors are wound. So you have the laminations right here. So these laminations, when they're cut, if I were to remove the plastic, you would see a T. So it's round, and then there's sort of a T, and then all the little plates are stacked up together. I mean, it's easier to take these laminations and just take a sheet and then punch them and then put them together than it would be to try to mill all of that out. That's the reason why you have these laminations. But that's what the inside, if you've ever wondered what the inside looks like, that's what it looks like. Let me see if I can improve the angle. Roughly. Oh, there we go. There we go. You can see the T right there here on the top. And then that's where the windings go through. So, I'm not sure what the timing is on the motor, but if you want to do a different ESC where you can change the timing, for example, say you want a quick run ESC, You can always snip these off and then just change the bullet connectors and plug it into the other ESC. I mean, this is a sensorless motor, so it's not going to matter. You're going to have an A, B, C. Very good question about which one's A, which one's B, which one's C. I would have to test, and I do not see anything labeled. But what I can say is, well, based on this, let's see this wire. So if we put the little notch on the bottom,
the top wire is B, going that route. So then just left and right, you just have to figure out which one of those two is B and C, which would be easy. If you plug them in the wrong way, you can always just flip the wires around and you would be good. And sometimes you can tell because one way you'll have a little more power than the other way, so keep that in mind. The other option too is those bullets inside. Those are about 2mm bullets, so you can just get some 2mm female bullets, plug them in there, make your own little harness, and go that route. So that'd be the easiest way.
All right, so this is an example of a different rotor. Now this is off of a Hobby Wing. This is a 3660 series. That's why it looks this big. I mean, one of the differences that you can see is the epoxy that they use to cover the laminations. So you can see that there. But anyway, this is one of the differences. Now, if you were looking at a 2-pole, so this is a 4-pole. 1, 2, 3, 4. So that's a 4-pole. If you're looking at a 2-pole motor, many of the, for example, Hobby Wing G4s, they're perfectly smooth, very shiny. They look chromed. But that's something to keep in mind. So let's go ahead and do this. Now keep in mind there's no epoxy. So this is about 1574. 1574. That's nice. Let's look at the magnet size. 2877. 2874. 2859. Let's see how I measure it. 61. 70. And already went all the way around. All right. This looks pretty nice. So I'm going to go ahead and take a gauss reading, see what the gauss is. Okay, so ignore that reading, and the reason why is the sensors are right here. So the sensors are here and here. So I have to try to keep it the same distance from one side to the other and as close to the center as possible. That's why when I was doing this reading is close enough to give us a relative idea. So if I actually discard these, okay, so we're in the 800s. So I'm going to say 800s. So if I take the reading of positive, negative, yes, I'm altering. So I'm just trying to find the highest reading between them. If I were to just do this and then bring it down. All right, so my thoughts on the Traxxas BL-2s 3300 kV. I think this motor is a very good motor. It's a very well-built motor for what it is intended. And for me, I'm assuming the intention is to have a long-lasting, reliable motor that replaces the Titan 12 turn with more reliability. If you have seen my other tests with the motor, initially, this motor is not faster than the Titan. The Titan will actually take this motor on, but eventually the brushes will wear. And then the motor slows down, and on a brushed motor like the Titan 12, the RPM really depends heavily on the brushes. So you would have to take the motor, wash it, and then try to get some more out of it. I burnt mine up during those tests. It just can't handle heat. This motor can handle heat. Now the rotor, not the strongest rotor out there, I will be honest, but the rotor, they do go through quite a bit of effort based on that material that they removed to balance the rotor to make sure it's very well balanced. They do not use an epoxy to coat the laminations here on the magnets, which is fine, no big deal. The magnets are here, so we do have a 4-pole motor, 1, 2, 3, 4, on here, which is very, very nice. And I think that's the reason why it does well on the Slash. To be honest, I'd be willing to bet this motor probably does better on 2S than the VXL. I would just have to try to get my hands on my Brothers Fortec with the VXL. As far as the stator also, again, very well made. I'm saying it's a 13.5 just because I was counting turns. I don't think there's such a thing as a 14, but maybe next thing you know, it is 14. It's just you start and then you go, well, you do the half a turn, then it's 13 complete turns, and then you end here, which would be 13.5, but then if you add the other turn, it'd be 14, but then you start the next one. But anyway, so that's where you sort of sit. So if you have a 13.5 motor, this is going to be similar, except for the timing is different. I don't know what the timing is. I can't measure it. If I had to take a wild guess, the timing is very, very low. And the reason why is a 13.5 turn motor with low magnetism, at 45 degrees will generally yield closer to 4,000 RPMs. So you're looking at maybe 3,700, 3,800, closer to 4,000 RPMs. I would have to check my tables. Maybe it exceeds it, maybe not. But 3,300 kVs on a 13.5 motor, you're generally looking at something closer to 30 degrees of timing. So 30.5. So this thing is very low timing. I wouldn't be surprised if it were 30 degrees or even lower. It could be closer to, I don't know, maybe even, I don't know, I have no idea, but the timing's probably very, very low. The motor, I don't really think this motor is meant to be serviced just because of the bearings are pressed on. So the bearings do not come out easily like most motors. Most motors, the bearings will come out, they'll slide out really easy, and then you can pop the bearings out of the case, put a new bearing out. This one you cannot. I cut the front end part of the bell just to make it easier to remove. Since I was tearing out the motor anyway, that wasn't an issue. The rear plate, this is where the bearing sits, right in here. So the bearing sits in there, but in order to remove this, there's these little tabs you have to remove. I didn't have any tools that I could remove those small little tiny tabs, so I just went ahead and cut them off, and then I pried this out, which is how I bent it. But again, because I was planning on taking apart the motor, for me, it wasn't important to salvage the parts. Although, yes, you could say, well, you could have put everything together, all the windings together. That is true. The only thing is, because I was using pliers to pull this, if I damage the enamel, then it doesn't really work. Keep in mind, this wire, this isn't bare wire. This wire is coated so that it creates an electric field or a magnetic field. And the reason why is it doesn't matter how many turns you have. If you have bare wire without a coating, the current is going to find the shortest path that it can with the least resistance. Therefore, instead of the current going through all the windings, it's just going to cut across, which is why these are always coated. There's always an enamel that coats them, so it forces the current to go through, and it develops that magnetic field so that it doesn't just jump through the wires this way. It forces it to travel along the path of the wire. That's why turns are important. But this is what the motor looks like. So again, Gauss is in the 800s based on how I measured it. Not the strongest rotor in the world, so not the most torque. Timing is probably very low, and the reason why I'm saying that is usually the higher the Gauss, the more current to spin it. So you end up with more torque and less RPM, usually. I'm saying usually. So this one with so little Gauss, I would actually expect a little more kV, given that it's given how many turns it is. But again, it's not meant to be a rocket. So this is, if I had to take a wild guess, which would make total sense for me, and which is why I think this is a great motor, is this is probably just meant for, say, the weekend driver. Not even weekend. Maybe you take it out once in a month. You run 10 packs and the motor doesn't care as far as heat is concerned. It just keeps going and bashing. So this is for somebody that just wants something that's long-lasting, reliable. You just plug and play. You don't worry about temperatures, which is why I think this motor is brilliant. Because keep in mind, everything has a purpose. If you want a race motor, get a race motor. If you want a bashing motor, get a motor that's adequate for that. And the fan really does work. So this being said, I hope both this information was informative, hopefully very interesting. It was interesting for me. But I hope you enjoyed the video. Please subscribe if you have not. I'll catch you in the next one.
What? Oh, my hair! My arm! My rod!